Welcome to lecture 15. So, this is the last lecture of week 3. In week 3, we are talking about basic concepts of optimization part 1. As of now, we have talked about the optimality conditions for single variable unconstrained functions. In today's lecture, we will talk about optimality conditions for unconstrained multivariable functions. So, let us see the optimality criteria for unconstrained multivariable functions. Before that, let us take a quick review of gradient and Hessian matrix. So, gradient vector and Hessian matrix. We have discussed that gradient vector is nothing but a column vector where the elements are first partial derivative of the function with respect to each variable. So, if you have if you have a function f x where x has n components, that means x has a n vector x 1, x 2 up to x n, then the gradient will be a column vector with n components, and the components will be the first partial derivative of the function f x with respect to each variable in turn. So, del f del x 1, del f del x 2 up to del f del x n. Similarly, the Hessian matrix, which is a symmetric matrix, is second partial derivative of the functions. So, if you have a function with 3 variables x 1, x 2 and x 3, and if you consider all possible second order partial derivatives, you will have 9 components. So, the matrix of these 9 components is known as Hessian matrix. So, look at the Hessian matrix. First, this is symmetric matrix, and the diagonal elements are like d square f dx square, d square f dx 2 square and d square f dx 3 square. And look at this, then this and this and this and this. This del square f del x 1 del x 2 and del square f del x 2 del x 1 are equal. Similarly, this and this are equal, this and these are equal. So, a symmetric square matrix. The components are second partial derivatives of the function. We have learned few properties of these Hessians. They are summarized here one more time. The function f x will be strictly convex if the Hessian matrix is positive definite. Hessian matrix will be positive definite if x transpose H x is greater than 0, strictly greater than 0, or all the eigenvalues of the Hessian matrix is strictly greater than 0. The multivariable function f x will be convex if the Hessian matrix is positive semi-definite. The Hessian matrix will be positive semi-definite if x transpose H x is greater or equal to 0. In other words, all the eigenvalues of Hessian matrix is greater or equal to 0. The multivariable function f x is strictly concave if the Hessian matrix is negative definite. The Hessian matrix will be negative definite if x transpose H x is less than 0 or all the eigenvalues of the Hessian matrix is strictly less than 0. The multivariable function f x will be concave if the Hessian matrix H is negative semi-definite. That means, x transpose H x is less or equal to 0. In other words, the eigenvalues of Hessian matrix will be less or equal to 0. So, when I say x transpose H x, x is not equal to 0 here. So, we will make use of the informations on Hessian matrix when they are positive definite, when they are positive semi-definite, and so on and so forth. So, let us first discuss the necessary conditions for optimization of unconstrained multivariable functions. So, optimality criteria for unconstrained multivariable functions, what are the necessary conditions? The necessary conditions for x star to be a stationary point of a multivariable function f x at x equal to x star. Remember that x or x star, they are all n vector here, because the function f x is now a multivariable function. It has n variables. So, the necessary conditions for x star to be a stationary point of a multivariable function f x at x equal to x star are: the function f x is twice differentiable, at least twice differentiable. At stationary point, each partial derivative is equal to 0. So, this means that gradient evaluated at x equal to x star equal to 0. Each element of the gradient vector of f x at x equal to x star must be equal to 0. So, it means del f evaluated at x star is equal to 0. That means, del f, del x 1, del f, del x 2 up to del f, del x n equal to 0. So, this gradient vector is a null vector. And the Hessian matrix H is positive semi-definite when x star is a local minimum or relative minimum. And the Hessian matrix H is negative semi-definite when x star is local or relative maximum. So, let me summarize. If x star is a local, if x star is a stationary point for a multivariable function f x, then what is the necessary condition that x star will be an extremum, that means minimum or maximum. So, the first condition is that f x has to be at least twice differentiable. Second, at this stationary point x equal to x star, the gradient vector will be equal to 0, all the components of the gradient vector will be equal to 0. Third condition, that the Hessian matrix is positive semi definite when x star is the local minimum, and Hessian matrix H is negative semi definite when x star is a local maximum point. So, what are the sufficient conditions? For a stationary point x star to be an extreme point, that means maximum or minimum, the Hessian matrix H evaluated at x star must be positive definite when x star is local minimum point and negative definite when x star is a local maximum point. So, the sufficient condition is this, that the Hessian matrix will be positive definite and H will be positive definite for local or relative minimum, and Hessian matrix will be negative definite for local or relative maximum. And if the Hessian matrix is neither positive semi definite nor negative semi definite, the stationary point x star is neither a local minimum nor a local maximum, it is a saddle point. So, let me summarize one more time the necessary and sufficient conditions for multivariable functions, and I would like you to draw a parallel between the single variable function and the multivariable functions. So, for multivariable function, x star, if x star is a stationary point, then the conditions that x star can be a maximum or minimum are as follows. First, the fx has to be at least twice differentiable. Second, the gradient vector will be equal to 0. So, the first necessary condition, gradient vector is equal to 0. In single variable function, it was df dx equal to 0 at the stationary point x equal to x star. Then the other necessary conditions, that the Hessian evaluated at x star will be positive semi definite if x star is local minimum. In case of single variable function, it was the second derivative will be greater or equal to 0. This is necessary condition. Similarly, in case of multivariable function, if the Hessian matrix evaluated at x star is negative semi definite, the point x star is a local maximum. In case of single variable function, the equivalent condition was d square f dx square is less or equal to 0. So, for local minimum, the necessary conditions is Hessian matrix is positive semi definite for multivariable function. Equivalent condition for single variable was second order derivative is greater or equal to 0. Similarly, for local maximum, for multivariable function, the Hessian matrix evaluated at x star will be negative semi definite. Equivalent condition for single variable function was the second order derivative will be less or equal to 0. Now, let us come to sufficient condition. The sufficient condition that x star will be a local minimum for a multivariable function is the Hessian matrix will be positive definite. Equivalent condition for single variable function was the second derivative will be greater than 0. Similarly, sufficient condition for x star to become local maximum is that the Hessian matrix will be negative definite. Equivalent condition for single variable function was that d square f dx square or the second order derivative is strictly less than 0. In case of single variable function, we had point of inflection. The point of inflection was when the first non-zero derivative happened for nth order derivative and n is odd. In case of multivariable function, if a function is such that its Hessian is neither positive semi-definite nor negative semi-definite. That means the eigenvalues are not all greater or equal to 0, also not all less or equal to 0. In that case, the Hessian matrix is neither positive definite nor negative definite, or the Hessian matrix is neither positive semi-definite nor negative semi-definite, and we call the point as saddle point. For example, if the eigenvalues of the Hessian matrix is such that some eigenvalues are positive, some eigenvalues are negative, then it is neither positive semi-definite nor negative semi-definite, it is indefinite. The Hessian matrix is indefinite and the point is known as saddle point. So, now let us consider a Taylor series expansion about the stationary point x star of the multivariable function f x. So, we can write this expression using Taylor theorem. Note that x and x star are all n vector and we are considering x minus x star delta x as perturbation. Also note that del square f evaluated at x star is nothing but Hessian evaluated at x star. So, this is nothing but the Taylor series expansion of a multivariable function, it is in vector form. So, if f x star is the local minimum, then f x minus f x star is greater or equal to 0, because f x star will have the minimum value. So, f x minus f x star will be greater or equal to 0. So, if f x minus f x star equal to 0, then gradient of f x has to be equal to 0, because this delta x is arbitrary in the sense that it can be made positive as well as negative. See x minus x star, this can be made positive or negative. So, the gradient that means this term must be equal to 0. So, that f x minus f x star is greater or equal to 0. So, this is the first necessary condition, first order necessary condition for the local minimum. Also note that this term must be greater or equal to 0. So, that f x minus f x star is greater or equal to 0. So, this is Hessian. So, this is like x transpose h x is greater or equal to 0, that is the requirement. Note that this is nothing but Hessian. So, if you remember, x transpose H x is greater or equal to 0 is the requirement for the Hessian H to be positive semi definite. So, Hessian should be positive definite if x star is a local minimum. So, we get the two necessary conditions. One is the gradient evaluated x star equal to 0 and the Hessian matrix evaluated x star is positive semi definite for minimum to occur. So, f x minus f x star is greater or equal to 0, f x minus f x star is greater or equal to 0 when this term is greater or equal to 0, but if I want f x minus f x star is greater than 0, then this term must be greater than 0 and this is x transpose H x greater than 0, strictly greater than 0 is a condition that H is positive definite. So, if x star has to be local minimum, the sufficient condition is this, that the Hessian matrix is positive definite. Positive semi definite is a necessary condition, but positive definite is a sufficient condition for x star to become local minimum. Similarly, for local maximum, f x minus f x star is less or equal to 0 and considering the same argument, the necessary conditions for local maximum is the gradient equal to 0 and Hessian is negative semi definite. Similarly, the sufficient condition for local maximum is Hessian is negative definite. So, now let us take few examples. In the first example, we want to show that the necessary conditions are not enough to make a comment on optimality of a point. So, first example we take a two variable function f of x y equal to x s cube plus y cube. We ask the question, does the function attain minimum at 0 0? So, is 0 0 a minimum? So, let us first take the gradient 3 x square 3 y square, these are the components of the gradient. Let us take the Hessian. So, to take Hessian, this is del square f del x square, this is del square f del y square, this is del f del x 1 del x 2 and this is del f del x 2 del x 1. Note that this and this are same, both are 0. So, the Hessian matrix is 6 x 0 0 6 y. So, evaluate this at point 0 0. The function value at 0 0 is 0. The gradient vector at 0 0 is also 0 0 because 3 x square 3 y square are the components. So, 0 0. The Hessian is also all 0 zeros. So, the Hessian is positive semi definite. So, the point 0 0 satisfy all necessary conditions, but x equal to 0 y equal to 0 is certainly not minimum for this function. For simple reason, you consider, let us say consider a small deviation from 0, say x equal to minus 0.1 y equal to minus 0.1. So, x s cube will also be a minus negative quantity, y cube will also be a negative quantity. So, the function value will be less the function value at x equal to 0, y equal to 0, x equal to 0, y equal to 0, the function value will be 0. But even a very small negative value of x and y will have the negative, will have the function value which is less than 0. So, 0 0 cannot be a minimum point. So, the necessary conditions are not enough for optimality. Let us take another example. In this example, we will show what is saddle point. In this example, we want to analyze the function x square minus y square at x equal to 0, y equal to 0. So, apply the optimality conditions, evaluate del f del x, del f del y, del f del s equal to 2x, del f del y equal to minus 2y. So, there 0 at x equal to 0 and y equal to 0. So, the gradient is zero. The Hessian matrix can be obtained as this. So, the eigenvalues are 2 and minus 2. So, the Hessian matrix is neither positive semi-definite nor negative semi-definite. That means, definitely not positive definite nor it is negative definite, it is actually indefinite. So, the point 0 0 is neither minimum nor maximum, it is a saddle point. If you see the plot of the function, a 2D plot, if you see, this is what it looks like. It looks like horse saddle, and that is why the name comes saddle point. Let us look at example 3, which is a function of 3 variables. So, consider the function as shown, it has 3 variables. We want to analyze the stationary points, whether they are maxima, minima or point of inflection. So, take the gradient, set it equal to 0. The gradient will have 3 expressions, 3 components. 3 components corresponds to 3 expressions, which will all be set equal to 0. So, basically you have to solve these 3 equations simultaneously to find the stationary point, and you get the stationary point as x 1 equal to half, x 2 equal to half and x 3 equal to minus 2. So, you have a single stationary point, x 1 equal to half, x 2 equal to half, x 3 equal to minus 2. We need to check whether this is maximum or minimum or saddle point. So, find out the Hessian. All the components have been found out for the Hessian matrix. And you see that eigenvalues of the Hessian are minus 2 plus minus square root of 8. Square root of 8 is greater than 2. So, basically you have 2 negative eigenvalues, 1 positive eigenvalues. So, the Hessian matrix has both positive and negative eigenvalues. Thus, The Hessian matrix is neither positive semi-definite nor negative semi-definite, it is indefinite. So, the stationary point x equal to 0, y equal to 0 is a saddle point, stationary point x equal to half, y equal to half and x 3 equal to minus 2. This stationary point is a saddle point, because the Hessian matrix is indefinite. As a fourth example, let us consider the two variable function as shown on the screen. So, let us take gradient, it is a two variable function. So, the gradient will be del f del x 1 and del f del x 2, it will have two components, and if you solve del f del x equal to 0, you will have 5 stationary points as 0 0, 1 0, minus 1 0, 0 1 and 0 minus 1. So, now let us consider Hessian. It is a two variable function. So, Hessian will be 2 by 2 symmetric matrix, and we have to analyze all the 5 stationary points considering whether the Hessian matrix is positive definite or negative definite or positive semi-definite or negative semi-definite or indefinite at all of these 5 stationary points. So, let us start with point 0 0. The eigenvalues of the Hessian matrix evaluated at point 0 0 are minus 4 and minus 8. So, the Hessian matrix is a negative definite. So, 0 0 is a local maximum. The function value of 0 0 will be 2. Now, let us consider point 1 0 and point minus 1 0. At both of these points, you will have the same Hessian matrix, and the eigenvalues are minus 4 and plus 8. So, out of these two eigenvalues, one is positive, another is negative. So, Hessian is indefinite. So, 1 0 and minus 1 0 are saddle points. The function value at both of these 1 0 and minus 1 0 is 1. Next, we will consider point 0 1 and point 0 minus 1. Again, at both the points, we will have the same Hessian matrix. The eigenvalues obtained for this Hessian matrix are 0 and 16. So, this is positive semi-definite, because eigenvalues are greater or equal to 0. So, 0 1 and 0 minus 1 may or may not be local minimum, because only necessary conditions are met. The Hessian matrix is positive semi-definite, not positive definite. So, the points 0 1 and 0 minus 1 may or may not be local minimum. We cannot conclude if these are local minimum or not, because it is not positive definite, it is positive semi-definite. However, let us look at the contour plot. The 0 1 and 0 minus 1 are actually global minimum. They are not only minimum, they are actually global minimum. The function value is 0 for both of these 0 1 and 0 minus 1. And if you look at the function is sum of two squares. So, the minimum value that the function can attain is 0. So, point 0 1 and 0 minus 1 are actually local minimum as well as global minimum, but we cannot show that the Hessian matrix is positive definite here. However, by the analysis of the contour plot, we can conclude that point 0 1 and 0 minus 1 are actually local minimum as well as global minimum. So, as a summary, you have point 0 0 as maximum, 0.10 and -10 are saddle points, and 0.01 and 0.0-1 are local minimum, and these are also global minimum. So, with this would like to stop here.